Good morning, everyone. Here, I'm going to discuss about the stability analysis using the Bode diagram because uh, the most important thing in the control system is the stability. Because once you want to design any control system, first step is that you have to assure that the system is purely stable, or how much this is stable. That can be done with the relative stability analysis we have done in the previous classes. Now here onwards, we will discuss the stability analysis in the frequency domain, because frequency domain analysis gives some other kind of parameters other than the time response parameters already we have discussed. So here we will use the Bode diagram to get the stability, and to get the stability analysis using the Bode diagram, different parameters are to be considered and these parameters are to be measured accordingly, right? So what are the different parameters are of are most important? That is, first of all, the frequency domain parameter. Not only this is the parameter, these are the parameters used for frequency domain analysis using Bode diagram. There is also another tool in the frequency domain analysis, that is polar plot, that is Nyquist plot, and in all these plots also these are the main parameters. So we can say it the performance specifications in the frequency domain analysis. These are the basically performance specifications. So performance specifications are gain margin, number 2 phase margin PM, number 3 grain crossover frequency omega c. Crossover frequency means we can write it omega c, and suffix g is used to denote this is a gain crossover frequency, right? Next 4, that is phase crossover frequency. This is omega cp. So these are the main 4 parameters we need to understand clearly, and the procedure from the Bode plot by which you can get these parameters, and depending upon the values of these parameters like gain margin, phase margin, gain crossover frequency and phase crossover frequency, we can say or we can conclude that the system is stable or not. And here one of the important issues is that by using Bode diagram, what you have taken, we have taken the open loop transfer function. See, the beauty of the frequency domain analysis is that open loop transfer function is considered in Bode analysis, right? But by using the Bode diagram, once you will find these all 4 parameters and their corresponding range of values by which the system can be stable, we can say from the open loop transfer function analysis whether the system is closed loop stable or not. The beauty of the control system and beauty of the frequency domain analysis method, that means analysis of the stability using the Bode diagram, is that, or in case of you can talk it about polar plot or Nyquist plot also, that open loop transfer function is considered for analysis, but at the conclusion side you can conclude that the system is closed loop stable or not, right? So you need not to have any feedback mechanism, that means any kind of feedback system is to be considered. Not only that, because once we are talking about the closed loop system, that means the first idea which is coming in our mind is that whether the system is to be made first of all closed loop or not, but here there is no such requirements there. So see, these are the performance specifications of the frequency domain. Again, this is gain margin gm, phase margin pm, gain crossover frequency omega cg, and phase crossover frequency omega cp. Now we will just draw a arbitrary graph. That means for any system, maybe the graph will be like that. If the semilog graph paper gives you a view how the Bode plot, Bode magnitude and Bode phase plots are given from the Bode phase plot and Bode magnitude plot, we will study how to find out the gain margin and phase margin, and what are the values of phase margin, gain margin, omega crossover frequency, and phase crossover frequency and gain crossover frequency, such that system can be stable. Okay. See what we have considered. We have considered a Bode magnitude plot and a phase plot in the same graph, right? So just focus. I'm trying to focus on it. See, this is the Bode magnitude plot and Bode phase plot here. This part, the upper part is considered the magnitude plot, lower part is phase plot for a particular system, whatever may be the system. you can draw the Bode magnitude plot and phase plot corresponding to it, right? And see, the scaling is like, and from the this is your Bode magnitude plot actually. This is a line 0 dB per decade, this is minus 20 dB per decade, this line slope is minus 40 dB per decade, and this line is minus 20 dB per decade again. Now how to get, the main purpose is to get the gain margin, phase margin, gain crossover frequency and phase crossover frequency. So before going to get this value, first of all I will define what are these values. Omega Cg, what is this omega Cg? What is this? This is the gain crossover frequency, gain crossover frequency. Now gain crossover frequency means what? Gain crossover frequency means actually you have to see the gain crossover frequency means the frequency at which the gain is 0 dB. The frequency at which gain is 0 dB. You see the frequency at which gain is 0 dB, right? So frequency at which gain is 0 dB means what? Just from the, say for example, this is one XY graph and you know these values or this value, say graph is there, right? So the value at, for every value of X there will be every value of Y, and for example this point is your desired value, right? Say this is your 0 dB line. Now corresponding to the frequency, how you will get, that means where this 0 dB line will touch this line, that corresponds to a frequency. That frequency is known as the actually gain crossover frequency in Bode plot, Bode magnitude plot. So you see the one definition, omega Cg means the gain at which the frequency at which the gain is 0 dB. Now frequency will be calculated based on this table. 0 dB line, what is this 0 dB? 0 dB means this line, this point is 0. So we can draw a line, say here. So that means in this point on the magnitude plot the gain is 0. Here the all these points gain is 0. So that corresponds to a frequency. So this frequency is known as omega Cg. Clear? So omega Cg means, now look at from this side, that means at this frequency you are getting the magnitude 0 dB. So in other words, omega Cg, because this from the calculations from the graph you can see the value of this is near about 0.9. So here you get the omega Cg is equal to 0.9 radian per second, right? So this is 0.9 radian per second. Next thing is that omega Cp. These are the two parameters. First of all you have to find out omega Cp means phase crossover frequency. Phase is standardized with respect to minus 180 degree line. If you can remember, in the last class we have discussed that this minus 180 degree line we have calculated, or we have made the table phi versus omega in such a way, if there is a possibility of getting minus 181, if there is a possibility of getting minus 80.1, like that, that was our aim. That is why when we have constructed the table for phi versus omega, what we have done, we have considered that the 50 times of the largest corner frequency, such that if possible the phase curve may cross this minus 180 degree line. That was the purpose. So this is the frequency at which the phase is minus 180 degree line. So in case of gain, 0 dB line is the standard value, and in case of phase, minus 180 degree line is the standard one. So here we will find the same procedure. By the same procedure, that means frequency at which phase is minus 80 degree. So we have to first identify the point where the phase is minus 180 degree. So here you see the phase is minus 180 degree. So that corresponds to a point which is omega Cp. Here from the graph you can see this phase, that frequency omega Cp. Omega Cp is less than omega Cg actually. Omega Cg was that, omega Cp is this. So omega Cp that may be equal to 0.6 radian per second. From the graph you can get it, right? So you get the two frequencies. One is frequency at which the gain is 0 dB, that is the gain crossover frequency, and the frequency at which the phase is minus 180 degree, that is that is omega Cp. Once you get these two frequency, then also you can get the issue related to stability, but we have to find out all four parameters. Next, we have identified these two parameters. Now gain margin and phase margins are related to these frequencies, right? Next is gain margin. Gain margin is related to, this is related to omega Cp, right? That means gain margin means we have to calculate the phase crossover frequency. Again I repeat, gain margin means you have to calculate the phase crossover frequency, and phase crossover frequency is already calculated. Now this is 0.6 radian per second. That value is phase crossover frequency. That means the frequency at which the phase is minus 180 degree line. Now gain margin means how much additional gain you can incorporate to the system such that system is in the verge of stability. Verge of stability means, for example, additional gain. For example, additional 5 dB gain you are going to add with your existing system. Additional 5 dB gain. Once additional 5 dB gain you are using, then also the system is stable. If you add 5.1 dB just or slightly above this 0.5 dB, 5 dB gain, then the system will be unstable. So that is the marginal value. So marginal value of the gain which is actually required to make the system stable. Okay, so that is the gain margin, and gain margin means you have to find out the phase crossover frequency. And in this phase crossover frequency, what I will do, I will just make a line above. That means we will find the gain. We will find the gain at omega Cp, as simple as that. So at omega Cp we have to find a gain. So what is the procedure? Just in this frequency we have to find out the gain. So gain means you have to find out from this graph only. So just this line, say for example, at omega Cp you are getting the gain here, right? Here is your gain. So what is the gain? That can be determined from, you see, these positions. Sorry. So these positions, this is the gain. Say I can write it like A. Certain gain we can get, any gain, right? So this is above 0 dB line. Here in this case we are getting the gain above 0 dB line, and that may be, say here you see the gain. So gain at omega Cp, first of all gain at omega Cp. So gain at omega Cp, what we will getting, that is 10 dB above 0 dB line. So that is not the gain margin, right? Gain margin means what is the additional amount of gain you can add, marginal amount of gain you can add, right? So that is the actual definition of the gain margin. Now once you get this value, that is you see here the gain at this phase crossover frequency is, say, your gain. So once you get gain, that means the gain margin equal to 0 minus 8 dB. So minus 10 dB. What do you find? That means additional gain margins is minus 10 dB. So minus 10 dB additional gain you can add with the system such that the system gain becomes 0 dB. 0 dB is the standard gain of the system, right? That is the standard for stability analysis. So gain at omega Cp you have calculated by using this. Now at this frequency, what is the gain you have calculated? And once you calculate this value 10, so gain margin is equal to minus 10 dB. So that is the concept of gain margin. Now I am coming to the concept of phase margin. So similar to the phase margin is related to the gain crossover frequency. So phase margin, that is Pm. So this is your phase margin, that is related to omega Cg. That means you have to find out the phase at omega cg. That means what? That means what? Omega cg is here. This is your omega cg, right? Sorry, this is your omega cg. So 0.9. So at 0.9, what is the phase? So what is the phase means you have to consider this graph at this frequency. So in this frequency, this is your positions. You see, this is your point B. I can say it B, right? That means at this frequency, what is this frequency? This frequency is your gain crossover frequency. Gain crossover frequency. So at gain crossover frequency, you get the phase from this line. So this is your phase. So what is the phase? B. So phase B point, that point B is below the minus 180 degree line. And see, this is minus 180 degree to minus 270 degree. Say minus 200 degree, right? That is below the minus 180 degree line, right? So you see this below the minus 20 degree line. So what is the phase margin? So phase margin is equal to 180 degree plus of B. This is your phase margin. So what is the phase margin? 180 degree plus minus. So this is phase margin, that is equal to minus 20 degree. What you get? Phase margin is equal to minus 20 degree and gain margin was minus 10 dB, right? So you get the parameters value and the sign is very important. Either that value is positive or negative. That is very important. Here you are getting the phase margin is minus 20 degree. That means what? Additional phase. How much phase you can add to the system? You can add to the system minus 20 degree. So that much of phase you can add such that the system is its verge of stability, right? That is the concept of phase margin. So from this analysis, you see how to get the phase margin and gain margin and gain crossover frequency and phase crossover frequency. Now once you get all these parameters, so what is the specifications and how these specifications can be related to the stability? That is the next question, right? So what are the defined four parameters we have obtained? That is gain margin minus 10 dB. That minus negative is very important. This is minus 20 degree. This is very important. And these two values are related to each other. Means in the sense either omega Cg is greater than omega Cp or not. Here we will discuss these two issues. If phase margin and gain margin both positive, okay, any value 5 dB, 5 dB, 2 degree, 2 dB, 200 degree, 20 dB, whatever, if the phase margin and gain margin both are positive, system is stable. Then only the system is stable. If these are any one of this is negative, the system is unstable. Any one. If the phase margin is positive, gain margin negative, gain margin positive, phase margin negative, then also the system is unstable. So this is the condition for stability. Another condition of the stability is that if omega Cg is less than omega Cp, the system stable. What is the stability condition? We say omega Cg. What is this? Gain crossover frequency. If the gain crossover frequency is less than omega Cp, then the phase crossover frequency, the system is said to be stable. Here, now coming to our as the graph we have drawn for any system, that is given for any system. So for example, what do you obtain? This is negative and this is negative. So from this first criteria, this is criteria 1. This is, we can say, criteria 2. Okay. So criteria 1, you see this criteria, according to this criteria, gain margin and phase margin both are negative. The system is unstable. No issue. Next thing is that omega Cg, what is that? 0.9. Omega Cp, 0.6. So omega Cg is greater than omega Cp. That means the gain crossover frequency is greater than the phase crossover frequency. But the condition of the stability is that is the gain crossover frequency must have to be less than the phase crossover frequency. So if this is not happening here, so system is unstable again. So by both the criteria 1 and criteria 2, that is by criteria of the phase margin and gain margin, by the criteria of the frequency, gain crossover frequency, phase crossover frequency, in both the cases this is validated. So that is very simple. That means once you draw the Bode magnitude plot, you can draw the Bode phase plot for any kind of system. All the systems we have developed and all the systems we have solved, and by using that, each of the example you will take, for each of the example you will just go on calculating this phase margin and gain margin, and corresponding to the phase crossover frequency and gain crossover frequency is to be calculated. Otherwise you cannot calculate the gain margin of phase wise, right? So by using that rules, criteria 1 and criteria 2, you can get whether the system is stable or not, right? In the next class, we will discuss about that part. That means here we have considered the transfer functions, and from the transfer function we have drawn the Bode magnitude and Bode phase plot. But in the next section we will just do the reverse of it. That means that means if a graph magnitude plot is given to you for any system, for example any system, some experimental setup is made. By that experimental setup you have got some Bode magnitude plot. So what could be the possible way to find out the transfer functions, the type of the system, out of the system, and all this thing we will discuss in the next class. Okay, thank you.